Okay. So today I'm taking up the slot to tell people about what's going on with tracing FSDP and in general some of the new compiler X distributed directions from the distributed offsite. This is still in flux. So what I'm about to present today is my best understanding of the situation, but we can still change our mind. It's only been less than a week, and I would love to have all of your questions. So this is the doc I'm presenting. Let me just drop this in composability chat if you want to take a quick look. All right, so what's the context? So the story begins, I suppose, way back last year when we are saying, hey, PD2, let's make trading faster. Awesome. And we have this problem, which is we need to do something about distributed. But we don't even have the stack working for single node at this point in time. So we basically say, okay, well, we're going to work on single node training. And, some folks like Will and David and co are going to just figure out just enough to make sure DDP and FSDP work with Torch compile. Nothing fancy, whatever's possible. And, they got it to work. So we were able to go up on PyTorch conference and say, hey, PyTorch 2 is great. And by the way, it works okay with DDP and FSDP. But really the way that we made things work okay, so we essentially don't trace these things at all. We instead artificially graph break so that, for example, with FSDP, all we're really doing is torch compiling the insides of the FSDP blocks. All of the actual distributed communication and all of the management and prefetching, that's all happening inside of regular Python. So we don't have any visibility into that. And so one of the things that the distributed team was working on over the last year was this idea of distributed compiler, which has a bunch of goals, but the general idea is, it seems like a useful thing to be able to talk about graphs that, actually talk about distributed computation inside of them instead of having to always treat it externally. And this seems like a useful capability to have. Maybe you can imagine optimizing collective communication. Maybe you can imagine just, improving the performance by not having graph breaks. But, or maybe you could imagine, oh, I want some sort of auto parallel thing where I can take a model that is single node and make it work on multiple nodes. All sorts of possibilities, right? So it just seems like the kind of thing that we ought to be doing. Now, fast forward to today, and the current situation is basically there is a distributed compiler. It's not really, what's the diplomatic way to put this? It's not really clear what we're going to do with it. Certainly, it's not, we can't tell people, hey, let's just go ahead and replace, your existing code that's using FSDP or DDP with the distributed compiler. That's not really, the state that it's in. And over the offsite, we basically had an opportunity to basically chatter about, well, what are we going to do, right? Are we going to keep doing distributed compiler? To which the answer seemed to be not in the same form that we were doing it before. And so this new plan emerged. I'm calling it Tracing FSDP again. And this is a lot of ideas from lots of different folks. I'm just pulling all of the threads together. And the basic idea is we're going to try to capture the existing distributed code that is written in eager mode directly in Torch Dynamo. And so that's the idea behind this. And so I want to tell you more about it. Any questions so far about the background? Okay, so I just want to talk through a little bit of the sort of reasons why we want to do this, because there is a cost. So the technical approach is we have pre-existing code, for example, FSDP written in Python in PyTorch today, and we would like to trace through it so that we can capture all of it, collectives and all in FSDP, into a graph and then do something with it, which I'm leaving that unspecified as of right now. Now, FSDP is really complicated, actually. It does a lot of things. We can talk about what some of the things that it does. And, if you try to use PD2 on it, actually, like, a lot of stuff doesn't work. So there's also a bunch of work that we actually have to do this. So why do we think this is worth it? And this is one of the, parts that's not so, still a little rickety, I'll say. But here's the best argument for why we should do this. So one is that PyTorch 2 is all about making single node code run faster, but more than that, it's about running single node code in a sort of very, very structured environment, right? Whereas normally when you're running eager PyTorch programs, you have all of Python, you could be allocating random Python objects, triggering the GC. Once you're actually inside PD2, it's, you're just, queuing inductor kernels as fast as you can. And it's very, very simple Python code. And this means that you get more predictable performance, you get faster performance, and this actually matters when you're in a distributed setting. For when you have lots of nodes, doing a collective communication, so everyone needs to wait for everyone else to finish. You have a straggler, you have one node which did an unlucky garbage collection, everyone has to wait for that. So, problems with the runtime get amplified in this setting. This is one of the reasons why, the new C++ ad stack, is sort of pitching, hey, why are we doing these massive distributed system in Python? It would make more sense to do something in C++ where we have much more control over this sort of thing. Another big motivation for deciding to go on the eager implementation of FSDP directly is it's pretty battle tested, actually, right? There are a lot of people who are successfully using FSDP, and if you go and you say, hey, I want to just create a new distributed framework and please use mine, you've got to go through the same process of convincing people that, hey, this is a good idea. And that's a lot of work. And, we don't want to be in a situation where we have to work really hard just to get parity with the original distributed code. So if we start off with, the existing battle-tested code as our starting point, that substantially de-risks the portion of the problem, which is, but is it going to work in practice? And the answer is yes, because we're just doing the same thing eager FSDP used to do, but better. With PD2 on top. This is the entire value proposition of PyTorch 2. Similarly, but differently, people aren't necessarily using, PyTorch distributed, right? There's popular frameworks like Megatron and DeepSpeed. People are using those frameworks. And if we want a technical approach that can help these users, you need some sort of system that doesn't require you to take control of everything and, require people to buy wholesale into this thing, right? You want it just like torch compile, where you're like, hey, I've got my existing system, let me just torch compile this portion, and bammo, you get some improvements. This is the bread and butter of PyTorch 2. I think it's been pretty successful, and, I want to apply this same idea to distributed. And to get there, to actually support partial graphs, right, you need to start off with some code that actually can work in an eager setting. And so you need a thing that actually works in eager. You can have a very poor performance, perhaps, by starting off with a very simple, trivial eager implementation, which is a good idea, and we probably should do that. But if you want good perf out of the box, you want to start off with one of these already optimized eager implementations. Similar. Okay, on the flip side, if I think about this, with my PyTorch compiler hat on, improving Dynamo's capabilities so that it can trace through FSDP is sort of low risk in the sense that it is incremental. And the sense it is incremental is that when you look at what kinds of things we don't support in FSDP today, are things like backward hooks, The things like, some fancy Python state manipulation. Well, not that fancy, but, like complicated enough that we don't have coverage for it. It's stuff like I have a list. Where is it? Where's my list? Oh no. Okay, I lost my list. Oh yeah. They've got process groups, they've got streams, they sometimes directly manipulate storages. Like, in isolation, each of these is like a reasonable thing we might consider wanting to support in PyTorch 2. And so, we can bundle them up and say, hey, our goal is to trace FSDP, but the result is a bunch of general purpose improvements to Dynamo, which work in a number of other situations. This argument is one I stole from Jason Ansel. Some of the conversations we've had about tracing FSDP are along the lines of, but, will there actually be any performance improvement? Like, maybe we shouldn't do this at all. And, the answer to that is, hey, like, come on. Like, we can't even, what is it? It's table stakes to have some capture mechanism for distributed. You can't even you can't explore anything unless you have the basics in place. So, this is more of an infra investment than I want to make this faster investment. And this is important because, Andrew has done some experiments and looked at some traces, and if you look at sort of normal FSDP workloads, they're pretty well overlapped. So you're probably not getting that much performance from moving communications around. But that's besides the point. We're not here to make pre-existing workloads run faster, although I bet they will run faster because of overhead reduction. We're here to sort of set up the basis for anything interesting we want to do in the future. We basically don't have a seat at the table without actually having some basic capabilities like this. And more points. We've tried a bunch of other options, tracing the entire train step and then auto parallelizing it. We've also tried implementing FSDP via detensor. Some of these maybe you could argue we should invest more effort in, and I would love to have the discussion in this meeting right now. But there are a lot of things we've tried. Some of them we have given a pretty good shake of the stick at, and they haven't gotten us the outcomes we wanted. So in some sense, when I look at our situation here, I'm like, well, I don't have another choice. If I'm going to do something here, I have to do something, and I've tried a bunch of other things that haven't worked. Let me try another part of the design space we haven't done yet. And this is at the very end because it sort of varies how much you can actually do this. But obviously, if you can capture collectives in your graph, you can do optimizations on the collectives. And I just mentioned that, in FSDP, that, it's 5% maybe improvement you can get from this. But in other regimes like tensor parallelism, where it's very fine grained, there's often a lot of juice you can get out from the automatic approach in this case. Okay, so these are the reasons why we are doing this. So I'm going to pause again for questions, comments.
Okay, so if nothing else, I think one thing I would want to talk about is how do we approach DDP? That's something we haven't really talked much about, and I see Wancha's got some comments on there.
Oh yeah, that's a good question. So the complexity with DDP is that DDP is written in C++. Let's add a section about this.
And I guess we can include in the section there's DDP, and then there's using FSDP in no shard mode, which we could sort of make equivalent to DDP, maybe for compiled, but not for eager.
Mm-hmm. Yeah. So my take on this is if we want to trace DDP directly, we should report the C++ back to Python. I know this is feasible because DDP used to be in Python and it got ported to C++. So we just need to port it back. Um, I also think FSDP in no shard mode is an option. I don't know if I would necessarily recommend it to folks because, as you say, in Eager, it has less optimizations than DDP. I think that's sort of, we're just going to have to look at use cases for this. Yes, Wanshou.
Yeah, so for the first option, if we want to report C++ back to Python, does it mean like the C++ reducer just won't exist? I'm a little bit worried that the eager performance will just be like down, unless we have some way to recover the performance.
Yeah, so this is a good point. And as I said, this is one of the reasons why I don't want us to really worry about DDP until like we have a reason to worry about it, at which point we can like sort of look at what the exact constraints are. But my general thinking here is one of the reasons why we built PyTorch 2 is because a lot of the history of PyTorch is, oh, we did this thing in Python and it's too slow, and then we ported to C++. Horace, do you want to butt in?
No, I just have another thing I want to say afterwards.
Okay. So we ported stuff to C++ so that things get faster. And then when all this stuff is in C++, yes, it is kind of fast, but it's kind of a pain, right? Because all the C++ code is completely opaque to our end users. They can't go and read the source code easily or hack things up for whatever they want. So like one of the reasons why having a compiler is so useful is because you don't have to, build your system around these overhead constraints anymore, right? Like if PyTorch 2 had existed at the point in time when we were deciding whether or not to port DDP to C++, I would hazard that we would have seriously considered instead keeping it in Python and just saying, hey, to deal with the overhead problem, use PyTorch 2, which would remove a lot of the Python side overhead and hopefully get you to where you want. So that's kind of like we're pushing the Pareto frontier by having the option to compile so that you have the option to write things a little less efficiently in Python, but still have the same performance after you compile it. Horace.
Yeah, so the other thing I kind of want to mention about, a plausible reason why we might want to kind of embark on this process of using Torch compile is if we can make FSDP simpler / more usable to use. It's kind of my general impression that today, like FSDP kind of does have a decent amount of usability problems / like composability issues, and in general, it's just a lot of code. And one potential desirable outcome, perhaps, would be if we can make FSDP simpler, or like easier to use for end users. This is kind of an orthogonal, nice to have from the rest of these outcomes.
Well.
Yeah, so I would just say that is part of the plan, at least the simpler user interface part. I think that's like part of step 2, where we talked about after we traced flat parameter FSDP, which still has the UX problem. I think the primary UX problem is that you have to pick your own buckets or groups. And there are also some restrictions. You can only do them at module boundaries. And so the step 2 was, which is still totally exploratory, was to rewrite FSDP to do per parameter sharding instead of flat parameters, but using the same basic structure of FSDP that we just unlocked tracing for. So I think we do have this plan of getting a better UX there and automating the bucket stuff, but we don't have an outcome where FSDP is simpler. I think we've only made FSDP more complicated at the end of this 2-step thing. And that's something I also worry a little bit about.
But one thing I want to point out, which came up while I was discussing with Andrew, is that like if we are embarking on a rewrite of FSDP from the outset, then if someone is like, oh, but I want to add some new feature to FSDP, you're in this weird nether state where, maybe you shouldn't add the feature because we're rewriting it. So like, whole lot, right? But if you take your basis as we're going to start off just like faithfully tracing the existing implementation, maybe, here and there where locally it's easy, we'll like, relieve some pressure by simplifying things. Then, you can also simultaneously run a regular eager FSDP roadmap and, you can negotiate when you want to do the simplification. You don't have to do it now. You could do it in a little bit. Like you're not blocking all the other stuff that's going on the simplification. All right, I'm going to keep going. All right, so the rest of this presentation is just going to be a jumble of like sort of all the bits and bobs that like we have so far identified need to go into this. Harvest, your hand still raised. And these sections are not very well constructed, so I'm going to mostly talk through it. Okay, let's see. What is a good place to start? Okay, a good place to start is to briefly talk through what exactly FSDP does when you call a forwards. So I'm gonna assume you sort of know the basic concept behind FSDP, which is you've got sharded parameters, you collect them, do stuff, and then unshard them when you're done. And I'm going to talk through a little bit mechanically what exactly FSDP is doing to make this happen, because there's a lot of like moving parts in the implementation. So let me think. How do I want to structure this? Okay, I'm going to start with this in terms of things that you like, things you might not have realized FSDP is doing that it is doing. So some of the things that FSDP supports, one of the things FSDP supports is mixed precision. So in PyTorch, we have this thing called automatic mixed precision. It's a context manager. You turn it on, will automatically cast things to lower precision. That's not FSDP mixed precision. Because in FSDP, we're already doing stuff to parameters, right? We're taking them in shards and unsharding them on our node. And so this adds a logical interposition point to like make changes to precision. So FSDP has knobs that let you do this. So FSDP has a lot of knobs like this. There's also stuff for CPU offloading and stuff like that. I'm not going to talk about it anymore because it's sort of very orthogonal, but this is like part of the lots of features that were added to FSDP over time that, if you were trying to replace it, you would have to have an answer for. Okay. The other big thing that FSDP is doing is prefetching. So the concept behind prefetching is that, FSDP has all the parameters on different nodes. It wants to get them to your current node. It can start doing this process earlier before you actually need the data. And this is a good idea because you want the data to be there when you need it. You don't want to be like, oh, I need this data, and now you have to wait for the communication to happen. So all throughout FSDP, there's this sort of like very delicate dance, which is like at any given point in time, you're at some point inside FSDP's hooks because FSDP runs at the beginning and end of module boundaries. And FSDP has to answer a question, which is, hey, I'm about to run this module, so let me make sure that I've got all of the data I need for that. But also, what's the next module I'm going to run? And can I start loading the parameters that the next module is going to need while I'm working on other stuff? So that's just there's a bunch of Python state manipulation for keeping track of what's been prefetched, what hasn't been, and this is sort of stuff we have to trace through if we're dynamo tracing FSDP. Some other stuff that FSDP is doing, it's recording the order that you're evaluating parameters through the graph. Why do you want this? Well, it's because when you're deciding what to prefetch, you need to know what comes next, right? And in the eager mode, in general, you don't know what's coming next. So the way FSDP gets around this is it records, what order it saw things on previous iterations, so that the next iteration it can use this to make more intelligent decisions about prefetching. A lot of work on prefetching. This is very, very important, because you really don't want to be waiting for communication. Let me see. The big thing about FSDP is unsharding. So what do I mean by unsharding? Well, you start off with the parameters all on different nodes, and you have to collect them up onto your current node so that you can actually do compute on them. And this is actually very, very involved. So there are a few reasons it's very involved. So one reason this is involved is it's kind of complicated to actually do unsharding, because FSDP does this thing where you have a bunch of parameters, it concatenates them together in a single flat parameter buffer, and then chops them up into shards. So to reassemble the parameters, you have to take those chopped up shards, mash them back together, and then re-slice it into the actual parameters that are showing up there. And there's also some padding considerations you have to deal with when doing this. Remember, your parameters aren't necessarily going to divide exactly by the world size, so you have to handle that situation as well. Another complication with unsharding is FSDP has a constraint, which is that it needs to run the existing NN module without modification. The general pitch of FSDP is, you've got your existing PyTorch model, you wrap it in FSDP, and then suddenly it's parallel. And so to actually do this, we have to, actually take the parameters and swap them out for something else, right? Because the parameters are not going to contain the full data, because the whole point of FSDP is so that you don't have to store all the parameters all at once. So there's a bunch of, in the simple case, you just set adder to go and swap things out, similar to how the stateless NN module functional API works. But in some cases, we actually have to take the tensor impl that the parameter represented and directly overwrite that metadata. And this usually occurs when you're in some situation where you have multiple references to the same tensor and you need all of them to update. So if you just set adder, then if I have another, reference to the tensor in Python somewhere else, that won't get updated. Whereas if I do a data assignment, all the other pre-existing, tensor variables also will get updated as well. So this is pretty, if you just think about what kinds of stuff PyTorch 2 normally is able to deal with, this is also a bit of a, seems a bit complicated. Let me think. And that's everything I wanted to say here. Any questions, comments so far? Okay, so after you've collected all the parameters by unsharding them, yes, it's weird, collecting is unsharding, then you do the compute, and then when you're done, you need to free all the memory. And so this is also complicated for a different reason. So the reason that freeing the memory, okay, so normally you're like, okay, if I don't need a tensor anymore, can't I just, drop my Python reference to it and the tensor will go away and then I'll deallocate the memory? Well, yes, ordinarily, but in FSDP you have a problem. So the problem in FSDP is that when you are running your compute, you are generating an autograd graph. And the autograd graph may have saved references to parameters. And you don't want those saved parameters to actually stay live for the rest of your modules before you come back in backwards, because that usually will blow up all of the memory savings that you got from FSDP. What you want to do instead is sort of let go of them for a bit, and then when you come back in backwards, you gather them up from all the nodes again, and then you do the compute in that situation. And this is very similar to activation checkpointing, except instead of rerunning forwards to get your saved variables, with FSDP you're just doing communication to get your saved parameters. So how exactly are you going to do this? So FSDP predates pack and unpack hook. for Albin, who couldn't be here today, but I'm sure you're listening. So how are you going to do this if you don't have access to pack-unpack hooks, which are an autograd feature that lets you change what things get saved for backwards? So the way FSDP does this is that in reshard, what it does is it takes the storage for the tensor in question and it resizes it to be 0. Because resizing a storage actually will deallocate the data in question. And it will deallocate the data for all the tensors that may have references to it, including any tensors that have been saved for backwards. So at this point in time, you have a bunch of things that are saved for backwards, and they actually contain references to nonsense. Like it's not anything, it's not real data. And what FSDP will do is it will install a hook, the pre-backward hook, which will be responsible for unsharding the tensors and filling in the storages with their true data so that you can go ahead and actually do the computation on them. It's an interesting question whether or not FSDP could be rewritten in the more modern way using pack-unpack hooks. Both Horace and I made an attempt at this. Horace, you ran into some problem that wasn't entirely clear how to solve, right?
Yeah, the main thing that was tricky to me was you can't just it's like your hooks are happen on each value that is saved, even if it's a view of a different value. So it's not super trivial to determine what you should be doing with each each activation you have saved.
Right, because you want to do a per storage thing and then reconstruct all of you. So you could imagine some sort of complicated thing that commons up things that have the same views and then knows how to reconstruct that. But it's more complicated to do it that way. Let me think. Yes. And then the last part of FSDP is what's called the post-backward hook. So this is a hook that lives on the accumulate grad of a parameter. So the accumulate grad is essentially it's a fake grad function that gets called when you finally computed the gradient for a leaf node, something that you don't need to propagate any further. And all it does is it accumulates the gradient you gave it into the .grad field on the variable. So FSDP hooks into this because when you want to accumulate the gradient, you don't want to do this in normal way. What you want to do is, okay, so you've done a computation and the computation has been on the unsharded model. You've got all the parameters locally. And you don't want to save the unsharded gradients because they're too big. So what you want to do is you want to scatter them out to all the nodes so that you only hold on to the local shard of the gradient that you want to do in this situation. And so there's a pretty complicated hook which is responsible for making sure this actually happens. And it does other stuff too, right? For example, it does prefetching because you want to start prefetching for the next set of nodes you're going to do backwards for. Any questions? Did I miss anything? One more thing I'll say is all the while, FSDP is actually using multiple CUDA streams. So CUDA streams are this idea where if you have things that are using different resources on your GPU, because communication bandwidth versus compute SMs, they're different resources. So you can often run them in parallel. So if you run CUDA kernels on different streams, you can actually multiplex. Not multiplex. You can make sure both resources get occupied by kernels that are using different things. So FSDP actually uses 4 streams. There's a default stream, which you do the compute on. And then there's a separate stream for each of the communications The all gathers are on the unshard stream, and the reduced scatters are on the post backwards stream. Hopefully, these names are obvious for obvious reasons. And there's even a separate stream for dealing with full to low precision casts. I'm not really sure why this one has its own stream, but and it's very important that like these streams run concurrently, because for example, when we're prefetching basically says way ahead of time, I want to start loading data for the next thing I'm going to do. But I better keep making progress doing my local compute in this situation. Otherwise, it'll be worse than just waiting for the communication when you decided you need it, because you're waiting for it too early and you're using up more memory. Questions, comments? Okay, so let's talk about the plan. So what's the plan? Okay, so there are a lot of moving parts. They're kind of independent though, and I'm just gonna step through them one by one. So one prep step is we're gonna make sure we can do the tracing in a single process. One of the annoying things about working on distributed is to test anything real, you have to actually set up multiple processes which will talk to each other with collectives. This is terrible for debugging because you can't GDB your process anymore because there's multiple processes. You want a PDB, you need to sleep one of the process. Well, for PDB, I guess you can, check what your rank is and only PDB on one of them. But sometimes you have to sleep. If you want to attach a GDB after the fact, you have to sleep one of the processes so that it, waits long enough so you can attach GDB. In that case, if you're looking at your printouts, right, it's 2 processes worth of logging, spewing out. What a mess. So one sub-project, which Wancho and I have been doing, and it's actually all landed, is you can now run FSDP with a fake process group. And the fake process group essentially pretends it has done the communication, but it actually doesn't do anything and just gives you some garbage data. Is it garbage data? I think we just don't do anything to the tensor that you pass to us. And so in this way, you can run FSDP on a single process. You can't actually check for accuracy, but you can get through the entirety of your program, and you don't have to, torch run multiple process groups. I'm going to skip this for now. Oops. Okay. So I talked about all of the funny things that FSDP does for, making sure that when I save a parameter for backwards, I don't actually save the parameter. I want to save some sort of nulled out storage that I'll reinflate with an all-gather after the fact. So this is very, very annoying to trace because what it looks like in code is, you take out the storage object and you resize it to 0. What the heck do you even do in this situation? Do we really want to make functionalization support this? But Jason Ansel suggested a trick. And the trick is this. You don't actually have to trace in the resize 0. The resize 0 is here to make sure that you save you eliminate the data. But when we have converted the forward backwards into a joint graph, we can run dead code elimination. And so if we are able to see that the save for backwards parameter never gets used, we can just make sure we free it immediately without letting it propagate to the backwards. So the real question is proving that in the backwards, you're never actually using the save tensor data correctly. And here, functionalization comes to the rescue. If I do an in-place, a mutating operation on the storage from which the save tensors are derived views from it, then when I do the mutation to the flat storage, what I'll do is I'll produce a new tensor that represents the result that was written into flat storage. And then what functionalization will do is recompute the views for each of the tensors so that they come off of the newly allocated flat storage. So afterwards, the save tensors are actually dead. So we haven't tried this yet, but I'm pretty sure it'll work. And Jansel, although not completely convinced it will work, still thinks that even if it doesn't work, we can probably write a little FX pass to do this. So the plan on record for dealing with storage resizes is we're just not going to do it. We're going to drop that information and recover it in the compiler. This, by the way, is going to be a theme. One of the themes is that we are not going to, sometimes eager optimize the thing. We don't really care about it, so we're going to drop it and just reconstruct it ourselves in the compiler. Questions, comments about this? Okay, let's talk about dynamo tracing. So one of the things that we need to be able to do is we need to be able to dynamo trace the FSDP code. Today we don't. We special case the FSDP wrapper module and do something which doesn't involve actually going through the bytecode. So Vaz has been working on sort of like banging through all of the dynamo tracing, and there's actually a bunch of stuff that we need to do, like just plain features in Dynamo that we don't have support for. For example, if I have a user-defined object variable, so that's just a generic user class that I know nothing about, Dynamo doesn't know how to do setAttr and getAttr on it. But honestly, there's no reason it shouldn't know how to do that, right? We just need to properly model the dict on these objects and then have setAttr, getAttr do the right thing. Similarly, FSDP loves to use functools.partial. We don't support functools partial in Dynamo today. Just need to make it work. That's the thing. There is a question. Let's talk about it here. There is a question with regards to, so one of the things Dynamo's job is to do is to actually put things in the graph, right? Dynamo's job is to generate an FX graph, which we're then going to pass off to AOT Autograd to do tracing on. So what exactly should Dynamo put on the graph? And so there's actually a bunch of things that don't have obvious answers here. So for example, FSDP passes around these process group objects. So process group objects represent sort of who you are in the distributed computation setting. And they're kind of a pain because they're not traceable. You can't make FX through a process group. And even if you make effects through a proxy group, we wouldn't really know what to do with them on the back end. With traceable collectives, which is work that was done by, it's Will, it's you and Rodrigo, is that right?
Yeah.
Yeah. The way that they got around the process group tracing problem was instead of passing in process groups, you just pass in a list sort of describing the ranks that are involved with the computation in question. So Dynamo, if it sees a bunch of process groups, it needs to move the process groups around, but hopefully what it can do is then translate a call into a collective that takes in a process group explicitly into one of the traceable ones, which deals with very nice, simple to use 0, 1, 2, 3 ranks. So only Dynamo needs to know about it, and then at that point process group evaporates. Well,
yeah, so I don't think Dynamo even needs to do this anymore. We're looking at it, and so Traceable Collectives API layer actually already does this. What it does is it exposes APIs that accept either a process group or a desugared list of ints or whatever. And if it's the process group as input, it'll desugar it for you using some metadata and infra that's inside Torch distributed. So basically the eager code path already desugars process groups when calling further into the traceable collectives. So all Dynamo has to do is be able to traffic these process groups around through the eager code that already does the desugaring, which is a simpler problem than if Dynamo actually had to essentially create its own mapping or something.
okay.
And I was also going to comment on bullet 2, which is for work objects.
We don't actually use work jobs.
Right. So there's this async op or not async op for the existing collectives. And FSDP is using allGather and reduceGather in synchronous mode, which means there's no work object to deal with, which is great.
So the meta point is that there's a bunch of stuff that like Dynamo should support, and we're hoping to have a big list of things that if you helped us get them working in Dynamo, that would help us with FSDP end to end. Let's see what's going on. Okay, let's talk about gradient hooks, because this one's not totally settled. So I mentioned that FSDP makes prolific use of backward hooks. And here I want to make a distinction between backward hooks on intermediates and backward hooks on leafs. Backward hooks on intermediates are not too bad to deal with. The way you want to handle them is similar to how you handle a custom autograd function, although there is a problem which affects both of them, and I'll talk about that problem shortly. Hooks on leafs, though, are more problematic. The reason they're problematic is that they technically aren't part of any Torch compiler region. To understand why this is the case, imagine that I have a parameter and it gets used by a Torch compiler region, and it also gets used by a not Torch compiler region. The hook doesn't get executed until you're done running the backwards for both the Torch compiler region as well as the non-compiler region. So it's technically not part of the gradient hooks. So last week, our preliminary agreement was we were going to add some APIs to AutoGrad to like help you figure out if you could fuse in these parameter hooks later. But Horace has a new proposal for this, and Horace's proposal for this is essentially, hey, there's no reason to put FSDP's backward hooks on the actual leaf itself, because we can pretty much guarantee that no one is actually going to access the flat parameter directly. So the intuition is that we want to somehow restructure FSDP a little. So this is like, hey, modify FSDP to make things easier. Restructure FSDP so that the hook can run on an intermediate, which is guaranteed to run as part of the Torch compiler region. Horace, do you want to add stuff to this?
Yeah, it's more than just like that users will never should be never accessing flat parameter directly. It's also that the difference in semantics, or at least a simple example that I think of, is that if you let's say you call you pass an input through a module once and then you pass it through it again, so you call f of x or something like that. So the question is, in the backwards pass, should this hook run only once or should it run twice? And for something like DDP, it probably makes sense for it to only run once, because you only want to accumulate your gradients as soon as your entire backwards is finished. However, in the case of FSDP, it makes more sense actually, I think, for it to run twice, because if you're not running it twice, then what that means is that you're not going to reshard your parameters at the end of the first backwards pass of f, and so you're going to keep that alive. And so what I think you want to do is you want to call all gather and reduce gather twice, once corresponding to each of the times you use that module in the forward slash. That is perhaps a hard explanation to follow without a diagram, but basically the point is that I think this is not only easier to trace, but I also think it is more in line with what FSDP should be doing, compared to having it as a leaf compared to having the hook on leaf.
The status on this, though, by the way, is Andrew's tried a simplified version of this, and the obvious version doesn't work. So actually doing this change is going to be a little bit of work that needs to be worked out. There's a second problem, by the way. So the second problem is FSDP's backward hooks modify Python state, because of prefetching and stuff like that. So the playbook we did for custom autograd functions is we said in a custom autograd function, you're not allowed to modify Python state, and it has to be makefx traceable. This won't work directly in FSDP. So for handling that, there's sort of two schools of thought. School of thought one is that, well, we should run Dynamo on the backwards so that we can capture the Python state update and replay it. And school of thought two is maybe we can modify the hooks so that they're not updating Python state. We haven't really figured out which exactly we're doing, but this is one of the ongoing discussions. Let me think. I don't care about reparam. Uh, let's talk about unbracketed collectives. Okay. So, let's talk a little bit about prefetching. So I said the way prefetching works is we do an all gather, and specifically we do an all gather on the unshard stream, and then we do some stuff, and then later we wait on the unshard stream because we're actually ready to actually use the data in question. So if I want to compile this under the assumption that there is a graph break, or maybe even just the boundary between iterations, or even just the backward call between this prefetch and the wait, then I have a problem, because when I do the collective in inductor, the collective will be run on inductor stream, but inductor stream is not the same thing as the unshard stream. Yes, NYC.
I don't think we should ever graph break at that point. There's like only FSDP code between the all gather call and the wait stream, and it's like pretty much consecutive.
Then my question is, what about cross iteration? Or maybe we just don't care about cross iteration prefetch?
Wait, before we even get to cross iteration, Andrew, like, isn't there the case of prefetching that we do a prefetch before we execute the forward of this layer, we do a prefetch for the next layer?
Or
We don't do.
the complexity here is that, like, what Andrew is saying is that logically in the host side code, like in the CPU/Python side code, there's nothing in between like these two things. But due to the way that they're set up in the streams, like on the GPU stream, they overlap in ways. So like the prefetching is implemented completely with like CUDA stream semantics, basically.
Yeah, this is something I keep getting confused. So it sounds like what you're saying is that when we do the pre-forward for layer 0, we only fetch layer 0, and then we run forward for layer 0 on the CPU, and then we get to FSDP's pre-forward for layer 1, and that's when we do the so-called prefetch for layer 1, and then
yeah, so like
because of
when the CPU gets to the prefetch for layer 1, it is not done like going through the GPU for layer 0. And so at this point, if you place the all gather onto a stream that has no synchronizations with the mainstream, which to be clear is not the default behavior of collectives, then you can ensure that like CUDA will launch the stream whenever it's available, which is now because there's like spare items available or whatever. And so it can start the all gather for layer 1 before the compute for layer 0 has finished.
one thing that is the execution order needed for forward prefetching.
So, I mean, I can explain this more offline.
Okay.
Technically, there's both the implicit and explicit one. Where the explicit one actually reorders the order in which you issue the collective, and the implicit one is just letting the CUDA stream semantics take care of the fact that you can overlap a collective that was issued later in time on the host with computation that was issued like previously on the host. But there's cases like if you're very CPU bound and your CPU thread can't even get to that future all gather fast enough, we want to actually issue the next all gather before the current layers.
Wait, sorry, do you have an implementation of explicit prefetching?
Yeah, for both forward and backward. And for backward, it's very critical, and we have it on by default. Otherwise, the reduced scatter will block the next all gather.
Why don't we just do the explicit for both? Like, what's the downside of the explicit prefetching?
The explicit one assumes static graph. Right, like we're using the first iteration's order to prefetch for the next iteration, but for the backward prefetching, we're using the current iteration's forward, which we're actually able to observe, and we'll reverse that and do the backward prefetch.
Okay, so I think this is what made me confused, and I think I was reading the code for the explicit prefetch, and in that case, wouldn't you have to worry about a graph break occurring before the explicit prefetch of layer 1 that happens during layer 0, and then the actual wait for layer 1, which happens after layer 0 is forward?
Yeah, that makes sense. Sorry, I meant to only point out in that exact like code snippet that there should not be a graph break. But I do agree that in explicit prefetching there will be the opportunity for graph break.
All right.
So
but if explicit prefetching is a problem, I do see like it's possible to do it in the compiler.
Yeah, I guess that one last thing, should we just align on one? Is implicit prefetching the default, and should we be focusing on that for our tracing efforts, at least for starters?
So the only thing to mention is that for backward, we have to explicitly prefetch to get reasonable performance.
So we should probably just stick with the defaults, like make it aim for whatever, I guess, implicit forward, explicit backward. We should try to trace that first. That's my proposal.
Yeah, that makes sense.
Okay, we're out of time, but that's basically most of it. Any more comments, questions? Okay, well, thanks everyone. Yeah, this is fast moving, so there'll probably be more updates. Enjoy the weekend. See y'all.